STH hotspots. So in Kenya, we have three main types of STH. We have the so we have Ascaris, which is also known as the roundworms. We also have the Trichuris, which you can also call the hookworm, and also we have hookworms. So we are going to see how, or I'm going to demonstrate how we applied the statistical modeling to generate the first nationwide map of the STH-specific infection. So if I say STH, I'm just referring to the three in general, but we have the specific one, the hookworm, Ascaris, and Trichuris. So just an overview of the life cycle of STH. So the adult parasites infect or inhabit a part of some parts of the host intestines. We have the Ascaris and hookworm inhabiting the small intestines, and then we have the Trichuris inhabiting the colon, or the large intestine. So once here, the parasite copulate and oviposit, where the eggs are passed in feces and they are deposited in the environment. So once in the environment, and specifically in the soil, under favorable conditions, these eggs mature to the infective stage, which is shown here in this box. So the Trichuris and Ascaris mature to embryonated eggs, while hookworm now mature to filiform larvae. So these are the infectious stages. And so for Ascaris and Trichuris, the infection occurs by accidental ingestion of these eggs. What I mean by that is that where you take contaminated fruits or vegetables, or using hands or contaminated hands to eat. So that's how we ingest the eggs into our bodies. And then for Ascaris, for hookworm, sorry, the larvae penetrate the skin, majorly through barefoot walking. And then once it penetrates the skin, it travels in the circulatory system, where it goes to the lungs. Once in the lungs, it ascends to the throat, where it is coughed up and then swallowed, and then it ends up in a small intestine. And so the cycle continues from there. So, so the data we used in this study was obtained from a survey known as schistosomiasis practical and precision mapping. Schistosomiasis is also known as bilharzia. So the schistosomiasis practical and precision mapping is an evidence-based approach of doing impact assessment surveys. And impact assessment surveys is whereby countries or programs that have conducted at least 5 rounds of treatment are supposed to do a survey so that they can be able to assess whether they should change the frequency of treatment. So the schistosomiasis practical and precision assessment is a new method that has been introduced of doing this impact assessment. And so it was piloted in Kenya in the 32 counties. And so using this data, together with data that had been collected in other surveys previously, that's the data now we used in this study. So on the top row here, we see some points or some dots overlaid on the country map. So the dots are the schools where the data was collected in the 32 counties, plus other counties that the coastal and the western region where data had been collected in other surveys. So for each school, we obtained some pieces of information. The first information was the longitude and the latitude of the school, or where the school is located precisely. And then the second one was the total number of children who were sampled in each school. And then the third piece of information was the total number of children who are positive for each STH species, the specific STH. And then, so the positive here was defined as the detection of at least one egg in a stool sample of the school-age children. So from this point,
don't work because of an
I think we can.
So the body's immune system kills the cells that make skin. This is more noticeable on someone who's Arbor skin than it is with someone who has very little pigment.
Maybe you can just continue as.
Yeah, let me ensure they are muted.
Great. Sorry for that. I was saying for each school, we obtained 3 pieces of information. The first information was the longitude and latitude of that school, or the precise location of the school. The second one was the total number of children who were sampled in that school. And the third one was the number of positive. And the third one was the number of positive, or the number of children who tested positive for that STH species infection. So from this, we are able to calculate the prevalence, which was basically the total number of children who are positive out of the total sample. That's the way we are able to get the prevalence at school level. So, and it is shown in this. What we are able to see is that most schools have a prevalence of less than 2% because we've categorized them into these 5 categories. But we had some schools in some counties like Lam here, which had a prevalence of greater than 50%, or more than half of children who are tested for Trichuris in that school had at least 1 egg in their stool. So after that, we aggregate, or we find the average prevalence of the schools in each sub-county or ward. And these are demonstrated in the maps below for Ascaris, Hookworm, and Trichuris. So what we observe majorly is that for Ascaris, we tend to see them in the western region. For Hookworm, we tend to see them a higher prevalence in the coastal region. And then for Trichuris in the lower western and some parts of coast. But this is now the empirical prevalence without any modeled estimate. So we also investigated the distribution of this school level prevalence. And what we are able to observe is that for Hookworm, majority of the schools had a very low prevalence. So we have a very high light skewed distribution. But for Trichuris, we see that it's a bit spread, although not significant, but we see at least we have some values above 40. But for Hookworm, there are rarely schools with prevalence greater than 30. For Ascaris, we see that the prevalence is a bit spread, and we can see we can note a higher distribution of prevalence as the prevalence increases. So one of the foundational principles of geostatistical modeling is the Tobler's first law of geography, which states that everything is related to everything else, but near things are more related than distant things. So what this means is that for a spatial data set like the one we have for STH infection, we will tend, schools that are closer to each other will tend to have similar prevalence values as compared to schools which are far much apart. So that's the foundational principle of geostatistical modeling. And then when you have any spatial data set, the first thing before you actually do the geostatistical modeling is to first of all investigate whether your data exhibit this spatial structure, which we are saying that schools or locations that are closer to each other have similar values as compared to the ones that are further apart. So it is good to first of all investigate whether your data exhibit this spatial structure, because if it doesn't exhibit this spatial structure, then you do not need to do geostatistical modeling, and other statistical modeling without the spatial aspect of them would suffice. So one of the way to investigate whether your data set actually exhibit this spatial structure is by using a tool known as empirical variogram, which is given in an example here. So on the x-axis, we usually have the distance of your locations, and the y-axis, we usually have something known as the semivariance, or basically the dissimilarity. And so what we observe, for example, here in a situation where your data exhibit this or obeys this first law, this Tobler's law, is that as the distance increases, the dissimilarity of values or the prevalence of the phenomena that you are investigating increases up to a certain distance where it levels off or stops growing. At this distance, we usually call it the practical range. And what that means is that beyond this point or beyond this distance, the school prevalence at one location does not influence or does not correlate with another another school. So that's how we investigate it. We investigate whether our data exhibit this spatial structure. So how you do that is that you first of all, so for us here, we fitted a normal generalized linear model to our data. Then we extracted the residues, and using these residues is the ones that we try to see if they exhibit this pattern, because if there's no spatial, in the absence of spatial correlation, we would expect the residues or the pairs of the residues to just fluctuate randomly, and in the presence of the spatial correlation, we expect that the differences at shorter distances to be very low and increase as the distance increases. So one of the formal ways to test whether this actually happens is by calculating the 95% tolerance band here. And it's simple as such that if all the points fall inside this tolerance band, then it means that there is no spatial correlation, and you really don't need to do geostatistical modeling and other statistical modeling which do not really include the spatial structure or the spatial aspect of it would suffice. So for us, mostly in all the STH species, we saw that the points were falling outside the 95% tolerance band, and we moved on to do geostatistical modeling. So just as we model in other areas, it's always good to include some covariates, which help us not just in explaining the spatial aspect of our prevalence, but also to help us understand the drivers of this STH distribution in the country. So we obtained a sort of covariates, of course, from literature. These covariates have been shown to have a relationship with the STH infections. So one important thing is that these covariates were gridded. What that means is that if I take, for example, elevation here, we have that the country is divided into very small squares, each of 5 kilometer by 5 kilometer. And so for each square, we have the value of the elevation. So that's what we mean by gridded data set, so that we can be able to predict the prevalence at that level, or we can be able to get the prevalence for each square. And so the word for this is known as raster files. So that's how we obtain the covariates. And then we obtain around 11 covariates, and the 12th one here, the population under 15, was used now to do population weighted prevalence, when we are aggregating from this very high resolution to the different administrative levels that are required. So then we investigated the relationship between our covariates and each STH species STH prevalence. So what you can see, for example, in Hookworm prevalence, there is no really linear relationship between our covariates and the Hookworm prevalence, because these lines tends to be flat mostly, except, for example, in relative humidity, but the linear relationship is quite weak. And so this was also observed in the Trichuris prevalence, where on the x-axis, of course, we have the covariate, and the y-axis, we have the logit prevalence. And the reason for investigating this is that one of the assumptions of the generalized linear model, because the statistical model is an extension of the generalized linear model, is that we should have a linear relationship between independent variables, or the covariates, and the logit prevalence. So it is important to investigate this before moving forward. So we also know that in Trichuris, also we didn't have very strong linear relationship, but when it comes to Ascaris, at least we could see some linear relationships amongst different covariates. For example, the NDVI, precipitation, relative humidity, soil temperature, and the others. And so these phenomena has also been studied elsewhere in other research, where we find that if the prevalence of what you are studying is very low, then it becomes quite difficult to estimate the relationship between covariates and the phenomenon. So given what we've seen that for Trichuris and Hookworm, we didn't really observe a good linear relationship. We set out to do an automatic variable selection process, and to account for that lack of linear relationship, we employed a two-step algorithm. And so the first step here was to, of course, remove the correlated variables. After removing the variables that had a correlation of above 0.9, we remained with about 10 covariates. So for each of these, we investigated 4 forms. The first form was the original form. The second one was the random walk of order 1, and the third one was random walk of order 2, and the fourth one was we categorized the covariates into using the 25th, 50th, and 75th percentile. Now these random walks are way toward non-linearity in our model, because we used R, and specifically we used the package known as inner, and that's how we are able to add non-linearity. Basically, random walk of order 1 is like using the broken sticks, using the frequencies approach, and then random walk 2 also is a way to add non-linearity, but now the curve becomes smooth instead of being so sharp at the nodes, or where the relationship becomes a curve. So what that means is that, for example, if it's elevation, we had 4 forms: original form, random walk of order 1, 2, and then 4. And then that we extended for all the 10 covariates. So the first step is now to choose amongst the 4 forms, which is the best functional form, and we use the cross-validated logarithmic score to do that. So at the end of the first step, we have that we have a mixture of 10 variables, which are a mixture of original walks or random walks or categorical variables, depending on what the model said is the best functional form. So once you get these 10 covariates, we then run model for all the combinations of those 10 covariates. So we ran geostatistical models for 1 covariate, 1 and 2 covariates, 1, 2, 3 covariates, all the way up to a model that had all the 10 covariates. And also we chose the best model as the one that had the lowest logarithmic score. So after doing that, we are able to get the model, or we are able to get the model that had the highest predicted value, and we extract the covariate that were in that model. So for Hookworm, we had elevation and relative humidity, and the best functional form that was chosen was for elevation was categorical, and relative humidity was the original form. For Trichuris, we only chose 1 covariate, which was the NDVI, and it was in categorical form. Then in Ascaris, we had the NDVI, precipitation, and soil temperature, and all of them were in the original form or in the linear relationship. And this also confirms what we had seen in the empirical plots. So after doing that and running the geostatistical models, we were able to predict the prevalence at high resolution. And so what you observe here on the first map on the left, we have the lower credible interval mean. Then on the in the middle here, we have the mean prevalence. Then on the map on the right, we have the upper credible interval. So as I had mentioned earlier, the country is divided into very small squares of 5 by 5 kilometers, 5 by 5 kilometer, and for each we have the prevalence for each value, but we overlay with the counties just to see where these boxes fall under. And so after getting that continuous prevalence, we categorize them into this order. And so what we observe for Hookworm is it's majorly in the coastal regions, and this could be because of the sandy soils, which facilitate the mobile Hookworm larvae. and then and also due to high humidity and precipitation in these areas. Then we something here. Then we had the Trichuris. Then we had the prevalence of Trichuris, which we observed that it was majorly in the lower western regions and also in the coastal regions. But we see that the prevalence, at least we have some areas where we have quite a high prevalence of Trichuris. For Ascaris, we observed that this prevalence was something that is coming up in my screen. Just a moment, that is quite disturbing. Why is this coming up? Okay. So as that's been checked, we can continue. For Ascaris, we observed that it was majorly in the western region, and this could be attributed to the high humidity in these regions. Then now, after getting the prevalence at very high resolution, it's mostly when we want to do a intervention or policy, we really don't do it at very high spatial resolution. And so sometimes we would want to aggregate that prevalence to at different administrative levels. For example, if you require a village or a sub-county or a ward. So we aggregated the prevalence at the sub-county level and also accounting for the population aged between 5 to 14 years, so that the prevalence that we get after aggregating is population weighted or accounts for that population. So what we observe is that the Hookworm also is also prevalent in, we had some sub-counties with prevalence to 2% prevalence between 2 and 10%. And then, but we didn't have sub-counties with any higher prevalence. And then for Trichuris, we observe also in the lower western region, and also we at least in this case we had some sub-counties with prevalence between 10 to 20%. And then for Ascaris, also the highest we had the prevalence between 10 to 20%. Then on a national level, the Hookworm was around 0.6%, Trichuris at 1.4%, and then Ascaris at 2.8%, which means that Ascaris was the most prevalent and it was most prevalent in the western region. For us to be able to target intervention, we need to see which of these areas have a high risk of exceeding a certain programmatic threshold. And for us, we chose, for Kenya, we have a threshold of 2%, where if all the prevalence is less than 2, then we say we have eliminated, we have achieved elimination as a public health problem. And so we set out to investigate which of these areas had a high probability of exceeding this 2%, so that we can be able to target interventions in these areas. And so we saw that most of the areas around the Lake region or Western had a very high probability of exceeding 2%. And then for Hookworm, mostly it was areas in the coastal regions, and we can actually be able to get the specific sub-counties or the wards that had this high probability. And then for Trichuris, of course, we can be able to see the areas that had this high probability of achieving 2%. However, it's good to know that at 10%, which is the WHO's threshold, we had less areas that had probability. We had less areas that had a higher probability of achieving or not achieving, but exceeding this 10%, where especially for hookworm, we didn't have very high prevalence. We didn't have high probability of achieving or exceeding this 10%, and mostly it was between 0 to 0.25%. Now, finally, in any model, you need to trust our model, and therefore we did a cross-validation model to see how our model performed. And so how we did that is by holding 75% of the schools for training and then 25% for testing, and we repeated this for 4 times. And then we calculated some metrics such as the Pearson correlation coefficient, we had the root mean square error, we had the MAE and MSE. And so what we observed is that the model for hookworm performed suboptimally, and this could be explained by the very low prevalence that we saw, or the distribution, the highly skewed distribution that we observed earlier on. So some key findings that we got is that the most prevalent STH infection is the Ascaris, then followed by Trichuris. We also observed that Ascaris is mostly concentrated in the western regions. And then we also observed that the hookworm prevalence remains relatively low. And what can explain the high prevalence in Ascaris and Trichuris is by the way human gets infected with these 2 STH infection, which is majorly through ingesting the eggs. So that method could attribute to the reason why the prevalence of these 2 STH infection is still high in the country. This level, I would like to stop at this point and say thank you very much for listening to the presentation, and then there come the question or comments on this, and to mention that for the data that was collected, for more information on what we have done, you can use this link to get the paper, and also to another way to play around with or to interact with the data that we collected in the cytosomasis practical and position assessment. You can use the link to this this dashboard to view other data that you have collected, including wash data, snake bites, and all that. Thank you very much.
Thank you, Brian. Thank you for that session. And I hope you feel better very soon. Yeah, so we move to the Q&A session. And please post on the chat or raise your hand if you have any questions, or just unmute and ask. Florence.
Yeah, thank you very much, Brian. That was very intense, especially for program technical officers. But then I just wanted to allude that, I don't know, I'm just looking at the data and how STH infection is going lower in the country. And I think also we could attribute that to the control efforts by mass drug administration using albendazole, and especially within the coastal region where we've had control interventions for quite a long time. I can say one of the contribution apart from the environmental factors is the fact that there has been continuous control efforts to reduce the infection in these particular areas. I think I just wanted to add that. I don't know whether you agree with that, Brian, but I felt it's such a good contribution to what we are seeing today and the efforts that have been put in place. Thank you.
Thank you, Dr. Florence, for that additional comment. And it is true, I also agree that controlled efforts or the intensive efforts that have happened in the country over time has really contributed to this, the rolling of prevalence over time. And I think if we now incorporate incorporate this evidence, we can be able to even capture those hotspots that are remaining, and even to continue to do the targeted interventions and be able to eliminate the STH infections. Thank you.
Thank you, Brian. This is Gideon speaking. Nice presentation, really informative. Just a quick question. Maybe, and forgive me if I'm taking you back in terms of if you'd mentioned it, like for your analysis, have you identified like what are the key drivers of the infections for this? Can the analysis identify
we
this?
can't hear you. You're not audible well.
Okay, let me write the question in the chat.
Okay. As you write your question, Jeannie Victor has asked a question about, please, which geospatial modeling technique was used?
Thank you for that question. And if I get your question, is the geostatistical modeling or the model-based geostatistical modeling, where you have an extension of the normal generalized linear model to include now the spatial aspect of it. And I think if the answer is not very substantial, we can link up after this to see the specifics. Thank you. I hope I've answered your question.
As we wait for Givinji's question, anybody else with a question, please just unmute and pose a question. Or just post on the chat. We have enough time for the questions. Gideon's question is on chat. I think, Brian, if you can see that, you can address to it. I can read it for you.
Okay.
Nice work and very informative session. Can your analysis show what are the key drivers of infection for prevalence predicted?
Yeah.
Thank you, Jeffrey, for that question. And yes, the analysis can show which are the main drivers, and especially using the covariates that we have used, we can be able to see where or how they relate to the prevalence. Like if we have a high place, what is happening to the prevalence? If we have a low soil temperature, what is happening to the prevalence? It's just that we didn't extract that data in this study, or we didn't present that data in this study, but it is possible to do that actually. Thank you.
Next question. Anybody with a question, please unmute and ask, or just post in the chat.
Hello, Brian. I don't know if you can hear me.
Yeah,
Yes, we can hear you.
Yeah, my name is Felix. I'm a geostatistical modeling scientist also, based at Aga Khan University. That was a very interesting presentation, and I had a few questions about the accuracy of your geostatistical model, especially when you go down, maybe to, because I heard you talked about wards and maybe villages, and also since you talked about the gridded rasters were at 5 kilometers by 5 kilometers, which to me was not very high resolution, because I would imagine if you wanted to go lower, maybe you would get high resolution rasters at maybe around 30 meters or at least a kilometer. Then my second question, that was the first question about the resolution and how accurate the model is when you go down below maybe the counties or the sub-counties. My second question, very quickly, I noticed of all the covariates you used, one was conspicuously missing, especially the wealth or the socioeconomic indicators, which I would think would affect the prevalence of such infections. In particular, we've got one from Meta, the owners of Facebook. There's what we call the relative wealth index. If you would maybe consider in future models and see how wealth plays a part in the prevalence of the infections you've shown. Thank you.
Thank you very much for those questions and comments. I really appreciate. On the first question about the resolution, it is true that we can actually go up to 100 meters resolution. And so the reason we chose 5 kilometers here is because also sometimes when you go to very high resolution and then the distribution of the schools that you've got, sometimes it's good not to go to the highest resolution because of some challenges that you might face in that case. Specifically, what I mean by that is that the uncertainty sometimes might increase as you increase the resolution, but we didn't really test whether we had higher uncertainties when we did very high resolution. And so we just went with what most previous research have predicted that, but it's something that we can look at. And then with regards to the accuracy of the ward level, for example, or village level aggregated prevalence, I do not have information on how the accuracy changes as you change the resolution at which you predicted the prevalence, but also how we overcome that is by including the confidence interval, the credible intervals for inhibition approach, or also or basically the uncertainty to tell for example, the people who are using this data is that, well, we predicted this at ward level, but it could be anywhere between 10 to 20. So that's how we now be able to overcome that challenge of accuracy, because we have that uncertainty, so that it's just being honest about our model, so that when you're using the data, you know the kind of confidence that you have when you're using the data. And so the other part of the socioeconomic indicators, it is true that we really didn't include some important socioeconomic indicators. One of the challenges we had is the availability of these socioeconomic indicators at the graded level. And so some of them would require us to do geostatistical modeling to predict those socioeconomic indicators at that high level, at a very high level resolution. So that's why that was one of the reasons why we didn't include these socioeconomic indicators. But also, thank you for the input about the relative wealth index by Meta, and I think we are going to explore more on this as we continue to do this work. Thank you very much, and I hope I have answered your question.
Yeah, and Professor Thombe has also noted on the same in the chat, and he said, thank you, Felix. We'll look into the data you've cited. And then he adds, on the decision of the resolution level, I think you want to make predictions at levels that match practical implementation units. But thank you so much, Felix. And I've also seen Bosco. Bosco, I've seen your comments, and thank you so much.
Hello, sorry, the lights went out over here, so things happen sometimes. But I was adding to Brian's comment by saying that Professor Pomboi has posted a comment on in our chat, and he said we will look into the data you've cited, Felix, and also he talks about on the decision of the resolution level. I think you want to make predictions at levels that match practical implementation units. Also Bosco made a comment earlier, and Bosco, we note your comment and appreciate you taking part. Ginny, I think you have an additional question, and you're asking, please elaborate on the best fit during the model selection. Over to you, Brian.
Thank you, Ginny. And I assume that when you mean by best fit during the model selection was the process of selecting the covariates. Please confirm if you can just unmute. Okay. So in the first step, we use the cross-validated logarithmic score, whether, for example, I give an example whether you have the covariates of elevation. We have the original form, you run a geostatistical model. You also run a geostatistical model with the random walk of order 1. You also run a geostatistical model with random walk of order 2, and then run a geostatistical model. These are just univariate geostatistical models separately. Thank you for confirmation. Then the fourth one, you run a geostatistical model with the categorized covariate of elevation. So here you have 4 models, and they give you the cross-validated validated logarithmic score. And so amongst these, you choose the one that is the best. So if the model tells you that the original form is the best, you take that one. So you do this for all the 10 covariates. So in the end, you have some 10 covariates, which are a mixture of the forms. Some will have the categorized, some will have the original form, some will indicate that the random walks of different orders will be the best. So once you have this, mixture of 10 covariates, you run the model for all the combinations of the covariates. So we can have 2 to the power n minus 1 models, and here we had 10 covariates, so it's around 2 to the power 10 minus 1. So you run a model for each combination, and the combination, I mean that you could have elevation alone, elevation plus NDVI, elevation plus NDVI plus soil temperature, all those combinations, and then you also choose the model that has the best predictive power. So once you choose, so the model with the best predictive power, of course, you're going to be able to see which are these covariates that generated that model, and that's how we are able to choose the covariates used in our model. Basically, that model is the one that we use to predict the prevalence and subsequent analysis. Yeah, thank you. I hope I've answered your question. Thank you, Professor Dombo, for that question. About AI and as at now, I really don't think AI can replace geostatistical model entirely. And the reason for this is that there are some inputs to when you're modeling that are not very automatic and do not persist when you are doing different scenarios. And what I mean by that is when we show we show, I mean, we saw the variograms, we saw the distance at which there is no spatial correlation. So that value of the practical range, usually we need it when we want to, or when in the subsequent steps. And so it is usually not very direct, usually not very direct to get that range. And for example, here we used 5% of the extent of Kenya in the north-south direction, and to use it in the priors. So it will be very hard to automate that entirely without a human touch. And so that's why I'm saying currently I don't see it replacing us completely. And the other question of, do you see use case for AI and statistical modeling? I think that's something to think about. Yeah, thank you.
Awesome. So if we don't have further questions, I think we will end the session here. And thank you so much, Brian, for the session. It was great, despite you being under the weather. Thank you. And also thank you, the attendees, for making time for this. If we don't have further questions, I'd like to end the session right here. Thank you so much and have a nice day.
Thank you very much. Bye-bye.
Thank you. Bye.
Bye, Brian.